Alright, today we're going to be talking about atomic theory 2, and this material is a good bit deeper than what we've learned in pre-AP about the structure of the atom. So follow along. I'll try to do the best job I can explaining it, and then I can direct you to some more resources as needed. So let's pick up with waves and light, which is the first portion of this, and then we'll move in to the other topics which you see here. First of all, talking about waves. So waves are just traveling disturbances, basically, but they travel in some pattern for the most part. And so in a wave, we have the wavelength, and that's going to be the length from the crest, which is the top point of the wave. So there's a crest, to the next crest, which you see there. Now it could also be from the trough, which is the low point, to the trough. So that length would also be a wavelength. But the properties of a wave really depend on its wavelength, which we'll see as we move into the next slide. Here you see the first wave has a long wavelength, and the second wave has a much shorter wavelength. It says that the first wave is low frequency and the second wave is high frequency. So in terms of a wave, the frequency is how often it comes past a point. So if you think about this wave traveling with this long wavelength, the wave is only going to pass a point. Let's just say we had a point here. Okay, and you can imagine the wave coming by. That wave is only going to pass that point a certain number of times in a second. But this wave would come by much more often. So a long wavelength is going to result in a low frequency, whereas a high wave or a short wavelength would give you a much higher frequency. So the definition of frequency and then the symbol, which you see here, frequency is the number of times a wave repeats itself per second. So to calculate frequency, it's the number of waves that come by divided by the time that it takes them to come by. So the unit for frequency is 1 over seconds, okay, which is also written as seconds to the negative 1 power, and that is also a hertz is the unit we use. Okay, so those are all equivalent. The formula that goes with waves, this is known as the wave formula, is C equals wavelength times frequency. C here is the speed of the wave. In our case, we're only going to be talking about light waves. So the speed of light is always 3.8 times 10 to the 8 meters per second, approximately. If the density of air changes, that speed can change somewhat, but that's going to be our estimation for the speed of light. So then, if we know the wavelength or the frequency, we can solve for the alternate one. Notice your units here, though, because speed of light is meters per second. So your wavelength has to be in meters, and your frequency has to be in inverse seconds, which is also known as hertz. So we can do this example problem where it says find the frequency of green light that has a wavelength of 545 nanometers. Okay, so we have our equation, C equals wavelength times frequency. Okay, which of these do we know? Well, we know the speed of light, and this is green light, so we can use the speed of light, and then we know the wavelength, so we can put that there. However, the wavelength is in nanometers, so that's going to cause us some trouble. So what is a nanometer? A nanometer is 1 times 10 to the 9th nanometers equals 1 meter. So we're going to have to use that conversion factor to figure out how many meters that is, and from there we can find the frequency. So you see they set it up to solve for frequency by doing the speed of light divided by the wavelength and plug in those values. Now, to solve for meters, you'll see they just took 545 and tacked on times 10 to the negative 9 meters, because a nanometer is 10 to the negative 9 meters, or 10 to the nanometers equals a meter. So that's the conversion that they did there. And then they divided and their meters canceled, leaving them with 1/seconds, which is equal to a hertz. Okay? Very simple problems in terms of the math. Just remember to convert to make sure your units are the same. All right, why do we care about wavelengths in chemistry? Okay, why are we talking about wavelengths in light? That sounds a lot like physics. The reason that we're concerned with wavelength and frequency and light here is because that is the way that they really discovered the structure of the electrons within the atom, was by using light and seeing how it responded and how the atom responded. If you remember, if you were in my pre-AP class and we did the flame test lab, okay, the frequency and the wavelength of the light coming off of these atoms tells us a lot about the electron arrangement. What you can see here is that as the wavelength changes, the properties of the light are going to change. So if you have visible light and the wavelength changes, it's going to change the color of the light. But if your wavelength gets too short or too long, it's no longer visible to the human eye. So that's when you get things like radio waves and microwaves. This is known as infrared. This is what's used in night vision goggles. Ultraviolet, X-rays, and then gamma rays, which are used in cancer treatment. So these are all things that we're familiar with, and they are actually all light. They're just not all visible light. So don't worry necessarily about memorizing the order of these. Just know that how do we get these different types of quote-unquote light? Well, we change the frequency or change the wavelength. And remember, frequency and wavelength are related. So if the wavelength gets longer, like in radio waves, 10 to the 12th power is the wavelength there. Those long wavelengths are going to have low frequencies. All right. Now we're going to talk about the quantum theory of the atom. Okay, this is how we kind of understand the arrangement of the electron, is based on the quantum theory. So we'll start kind of laying the basis for that. First off, there was a man named Max Planck, and so we'll hear about Planck's constant, and that's where this came from. He hypothesized that the energy that was radiated from an object, the energy coming off of an object such as a heated stove, a light bulb, think of anything that's giving off heat, he's saying it's coming off in discrete units, and that's what a quanta is. So when you hear the word quantum, just think of little packets, discrete units. So what he was saying was you couldn't have any in-betweens in terms of your energy, but that it had to come off in these steps, okay, that you see here. So he's saying there's no way to get like this much energy given off. You can see where I'm drawing there. But you can have this much, which would be like 1 packet of energy. Or you could have like 2 packets, 3 packets, 4 packets. But you couldn't have like an in-between packet. Okay, so this is a quanta, okay, or a quantum. You have to go up in discrete units, which just means specific units. You can't go up in between like we think of energy, as you see here. Okay, so he's saying you got to go up a full quantum or not at all. And so why is that? Okay, why couldn't you have this in-between energy? It's kind of his question that he's trying to answer based on his hypothesis that you can only have this quantum of energy, not an in-between. We see a little bit more of that on the next slide. So this zooms in to what we really see when we look at energy, was that it was released in these quanta, and the height of each step is equal to a certain amount of energy for a frequency of electromagnetic radiation. So he comes up with this equation, okay, and here you have energy, which is our E, and then frequency, which we've already looked at as V. Now remember, we know that frequency is related to wavelength by this equation. So if we knew the wavelength, we might could find the frequency and plug it in here, right? And then frequency is related to energy. So we said when the wavelength goes up, the frequency goes down, and vice versa. And here we're seeing the frequency times some constant, okay, this is Planck's constant, always the same number, is equal to energy. So this means as the frequency goes up, the energy must also go up. So those are directly related. And vice versa, frequency going down, energy going down. So if we know the frequency in this unit, which is a hertz, times this constant, notice the units there, the seconds will cancel, so we will know the energy then in joules. And the energy is going to be in quanta, okay, specific amounts. All right, again, what in the world does that have to do with the atom? I thought we were talking about the atom. Okay, so here's where we're going to start talking about how that's related to the atom. So in the science world, they knew that certain metals would shed their electrons if you shine a certain frequency of light on them. Okay, so you've got light coming in, that's the green arrows you see here, and that's going to create the shedding of electrons. So those electrons would move from this metal plate over here on the left to the one on the right. And as they moved, of course, that's going to complete our electric circuit, and so then our lamp would light up. So that's how they knew that the electrons were being ejected. All right, a few facts. If they had low frequency light, low frequency, remember low frequency means low energy. And they shined it on the surface, no matter how long they shined it on the surface, even if it was like days they left it there, the metal would never give off its electrons. Okay, so what's up with that? They thought maybe if they just applied it for longer, it would cause the metal to give off its electrons, but nope, it never would. But if they increase the frequency of that light, so they increase the energy of the light to some threshold point, then the electrons were ejected immediately. So that kind of gives them the idea of this stair, because if they were along this point right here on the stairs, like they hadn't gotten this quanta of energy, then the electrons weren't going anywhere. But once they reached that level, that quanta of energy, just enough energy, then the electrons came off immediately and the lamp turned on. If they increased the intensity of that light and left it at the same frequency, then it would cause the electrons to come off faster. But they would still come off with the same amount of energy. So if their light had the same amount of energy and they just gave more light to it, like turned on 2 lamps instead of 1, but they had the same frequency, then it would just cause more electrons to come off. So higher intensity light, more electrons. If they then increase the frequency of the light, that would cause the ejected electrons to come off faster, not more of them. Okay, so let's go back and kind of review. You see these green waves? That's representing like a medium frequency. So that was enough frequency to eject the electrons. What if you apply more green light? So see all these green lights? That's going to make more electrons come off. Okay, what if you apply purple light? Okay, purple light has a higher frequency. Notice there's less purple light though than green light as we go from 3 to 4. So what if you apply a higher frequency but less of it? Like you only turn 1 lamp on again instead of 2, then you'll get less electrons, but they'll be traveling faster when they come off. Notice what that does to the light. So you'll see the lamp turns on and you have greater current if you have more electrons. The lamp turns on quicker if you have a higher frequency of light. Okay? So all this allowed them to discover something about the atom. All right, so what does all that tell us? Okay, so below a certain threshold, no electrons. Above that threshold, electrons came off suddenly. Okay, so here's the key. The frequency of the photon, okay, that's the light, if it is at or above a certain threshold, then its energy is transferred to the electron. That would cause the electron to overcome the forces of attraction that were holding it to the metal. But it had to be a certain amount of energy. If it wasn't enough energy, then the electron would stay bound to the proton. Remember, protons and electrons, positive and negative, those are going to be attracting one another inside the atom. So if you don't have enough energy, if you don't have that quanta, that packet of energy, if you don't have that much, then that electron's staying on the proton. Okay, there's that equation again that we saw with Planck's constant with our energy and our frequency. Okay, how is that related to the atom? So we know that the electrons are in the atom somehow, but remember we didn't really know how they were arranged. We just knew there's like a nucleus in the center and then there's electrons, right? Well, here we're going to try to make sense of this whole quanta thing based on where the electrons are. So Bohr comes up with this model based on what Einstein and Planck had found. So Bohr says there is a force of attraction between the electrons and the nucleus that result from opposite charge. Okay, we already know that to be true. We have our negative electron out here attracted to the positive nucleus. Now, why doesn't the electron just go in and sit on the nucleus? Okay, if they're attracted to each other. Why doesn't it just go and stick to the nucleus? It's moving so fast, okay, that keeps it from going straight into the nucleus. It's the same reason we're attracted to the sun. The Earth is attracted to the sun via gravity, but the Earth is not moving toward the sun. Instead, it's moving in the orbit around the sun. Okay, same thing for electrons. This attraction is based on Coulomb's law. Okay, this, if you learn anything in this class, learn the meaning of Coulomb's law. Coulomb's law says that force of attraction is equal to some constant K times the charge of the two particles. So in this case, it would be 1 for the proton, 1 for the electron. Unless you have lots of protons in your nucleus, so then you could have 2 if you're helium for your protons, 3 for lithium, so on and so forth, divided by the distance between those particles squared. Okay, so don't worry about this constant and just think about what this means. If the charge goes up, what's that going to do to the attractive force? That's going to increase the attractive force, right? And as the distance goes up, distance is on the bottom, what's that going to do to the attractive force? Well, if distance is in the denominator and it goes up, the force of attraction is going to decrease as the distance increases. So that means when we shoot light at a substance, if its electrons are further away from the nucleus, then they're going to take less energy to remove. So Bohr says these electrons are moving around the nucleus in a circular orbit. Only certain orbits are allowed, and each orbit is a fixed distance from the nucleus. An electron within an orbit has a set, here's this word, quantized energy level. So the reason that the electrons would only come off at a certain point, not before that, was because they are a set distance from the nucleus. So it took a set amount of energy to get them off. Okay, that's where that idea that energy is quantized comes from. If it was less energy than was required to knock this off of the atom, then nothing would happen. Okay, quantized energy level. These electrons that are further from the nucleus, they do not experience the same attractive force to the nucleus because they are shielded by those inner electrons. So you have the nucleus that's positive, and then you have a negative electron on the first ring, and then some more negative electrons on the second and third ring. Well, this negative electron way out here, it cannot feel the force of the nucleus as well because it's got this other electron in the way. And what do negatives do? They repel. So this negative is repelling that negative while this positive nucleus is trying to attract it in. So you kind of have competing forces. So this, what we call the shielding effect, reduces the attraction between this outermost electron and the nucleus. So that's going to be related to our ionization energy. So the ionization energy is the minimum energy required to remove that outermost, least tightly held electron from an atom. And so how do we find this? Well, we're going to shine light on the pure substance and then record how much energy it has when it comes off. And we can use this equation from Planck to calculate the first ionization energy. So here's the first ionization energy for several different elements, and we can go ahead and start talking about these trends. So you can see hydrogen and helium. Hydrogen's electron was much easier to remove than helium's, while lithium's electron was much easier to remove than either of those. Okay, and then you can see we're going across the periodic table to neon. Neon's electron's pretty tough to remove, but not as much as helium. Then sodium's electron is not hard to remove at all. Going across back to argon, pretty difficult. Potassium, not quite as difficult. Zinc, moving on up there, but nowhere near argon, neon, helium. Okay, so why? Why are some of these atoms' electrons so difficult to remove? And that's what we're going to look at. So here's the general trend on the periodic table. The ionization energy generally increases as you move across and decreases as you move down, or increases as you move up. Either way you want to say that. So why is that? First, let's compare hydrogen and helium. We said it increases as you move across the periodic table. So hydrogen's electrons are easier to remove than helium's. So why? Coulomb's law, Coulomb's law, Coulomb's law. So according to Coulomb's law, the force of attraction, okay, here's the equation again, is equal to K, Q1, Q2 divided by D squared. So what is different about hydrogen and helium? Well, helium has 2 protons in its nucleus. So this Q1 is going to be plus 2 instead of plus 1. And then the electron, of course, still has a -1 charge. Okay, the positive and negative aren't really important. The idea is that helium has twice as many protons, so its ionization energy, here's the exact values, but it's almost twice as much. So why then, if lithium has 3 protons, is it not 3 times as much? So if we look at lithium's value, lithium value is definitely not 3 times as much. It's much less than hydrogen, even though it has more protons. So why? Let's go back to Planck. Lithium's going to have a plus 3 instead of a plus 1. So why is it not 3 times as much? It must be this distance. Lithium's electrons must be further from the nucleus. Why would lithium's electrons be further from the nucleus than hydrogen and helium? They didn't understand. Okay, it didn't make any sense to them. So then Bohr had to look back at his model and say, oh, lithium's electrons are on another ring. So that's where we get this idea from. Hydrogen and helium, their electrons are on this first ring, but lithium's electrons are out here, further from the nucleus. And that's why lithium's electrons are easier to remove than hydrogen or helium. What about these? Okay, boron. Boron's electrons are harder to remove than lithiums. Carbons are even harder to remove. Neons are even harder to remove. So why does it increase as we move across? All of these are on the same ring, so distance really doesn't matter. It's now the protons. Boron has 5 protons, so that's a +5 attracting that electron. While carbon has 6 electrons, so protons. So it's a +6. And then neon +8. Okay, so if they're on the same row, they have the same rings, the distance is about the same. It's because those protons are pulling those electrons in tighter simply because you have more protons. Okay, again we see sodium versus argon. So sodium has 3 rings and so does argon, but argon has much more protons. So its ionization energy is going to be much higher than sodium. Alright, so let's look at the Bohr model a little more closely. The Bohr model really only works well for the first 3 rows, and so that's kind of where we'll focus. The first row of the periodic table has 2 elements. So what we call n equals 1, that first energy shell can hold 2 electrons. The second row has 8 elements on it, and the second energy level can hold 8 electrons. The third row of the periodic table has 8 elements, and the third energy level can hold 8 electrons. In fact, that third energy level can hold more than 8, but if we're just focusing on the first 3 rows of the periodic table, that is how we would arrange the Bohr model. So 2 on the first, 8 on the second, and 8 on the third as needed. So if we were doing beryllium, we would put 2 on the first and then 2 on the second, since beryllium is the second element in the second row. We have what are called inner and valence on our Bohr model. So the inner core electrons are located closer to the nucleus, and then the valence electrons are on the outer shell. So you can see sodium has 1 valence and 10 inner core electrons, while argon has 8 valence and still 8 inner core electrons. All right, we'll stop here and we're going to talk about PES next time, or maybe in class, which is based on what we've learned so far.